No, 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 stairs. Okay. So let me tell you about first what we are going to do today and tomorrow to make sure that we cover maximum portions which are going to be a part of your exam, and also ensuring that we understand what and where these things that you're studying is important from machine learning point of view, right? So from that point of view, the very first thing is okay. The very first thing is we have two different lectures to be covered. Lecture 8, lecture 7 actually, lecture 7 and 8. And lecture 8 that we have that I plan to cover next is basically very much related to what we have studied so far, like partial derivatives, gradients, right? It is all linked to that. So we'll be first covering lecture 8 today. The idea is to cover lecture 8 today, and tomorrow morning we'll be covering back propagation, auto differentiation. So back propagation and auto differentiation, right? So this part we'll be covering tomorrow. It's a very small part, but it's still very, very important from neural network point of view, because back propagation, is a way of back propagating the information uh, from the last layer to the first layer. Okay. So that's what is backpropagation, and we'll be studying that tomorrow. And how do we use chain rule to do auto differentiation is also linked. But from your exam point of view, I mean, I'm just telling you that mostly I have not seen questions asked from this portion in your exams. There are very rare chances when people have went ahead and framed a question from this topic. Majorly, it is, if you think of calculus, whatever we have covered in lecture 6, which is all about partial derivatives, gradients, and right. And what we are going to cover in lecture 8. Lecture 8 is about Taylor series, Taylors, and then maximum minima of functions using maxima and minima using Bayesian matrices. These questions are framed more. So you're almost certain to get a question on Taylor series, almost certain to get a question on maximum minima. Hence, we'll be covering these things before we go and deep dive into backpropagation. I'm pretty sure it is going to take the entire 2 hours of time today, because there are a lot of details. When I was going through the lecture, I found that there is huge amount of details which have been given here. So we'll learn about each one of them. What exactly is mean value theorem? What is I don't know whether you all remember. We studied mean value theorem during our school's 12th. I mean, whoever have done 12th or who have not done their 12th directly came in from Polytechnic, they might not relate to it. But if you have done your 12th around the same time, or this was eventually there in uh, all the school syllabus, if I remember, in ICSE and CBSE, and also this was one of the important topics in JE exams as well, right? So mean value theorem is really important. This is where we'll start with. I don't know how many of you got the intuition of mean value theorem, but mean value theorem is using which we derive Taylor series. Okay, should we start? Good. The syllabus for exam is from lecture 1 to 8. That's right. I have been sharing these problems. So what I'll be doing is I'll be sharing some problems today in the evening, which will be combined set of problems for lecture 7th and 8th. I mean, this session and the next session. Okay, the only thing that you'll be left with is the problems from lecture number 3, which is on uh, Jacobian is already there. I'll be covering that tomorrow, mostly. Jacobian is what in what forms it is used, but I told you Jacobian in the last class as well. Jacobian, the kind of problems that can be asked from Jacobians are rare, but from the intuition point of view and from the learning point of view, from the usability in terms of machine learning point of view, yes, Jacobians are actually very important. So we'll be learning their intuitions tomorrow. I would want all of us to concentrate on what is needed for all of us to appear in the next week's exam. I'll cover most of those topics, but I'll give you enough intuition about it. Jacobian is nothing but think of it as when you have a vector valued function, the output is a vector. You're just looking into the derivatives. The gradient of a vector valued function is always a Jacobian, right? So I will give you the intuition. How do we move from vector to vector to Jacobian, Jacobian to tensors, vector to matrices, matrices to tensors, and how does derivative helps you get to that state? Because that idea is very important. You will understand why processing using tensors is very fast today than processing via matrices, which used to happen, and via processing using loops as vectors, right? So all of those things are important, but I'll give you that idea, Parijat. Okay. So let's get started. I'll keep you muted for maybe for some time, and then maybe for next 30 minutes. I Whatever you see here, are you able to understand some of the portions of what is written here, in at least from this line, mean value theorem, which is that is a function is continuous and differentiable? Then what does this entire thing tells you? Anything that comes into your mind? I mean, look into it, read through it, understand, uh, or let's say, let me write something and let me ask you. Before mean value theorem, there is something called as Rolle's theorem. Okay, Rolle's. We used to call it Rolle's theorem. There was a girl in our school. We used to, because of that reason, we used to like, reiterate it as a Rolle's theorem. So, but anyways, so Rolle's theorem basically is the same mean value theorem. It has three conditions. First condition is if a function is continuous. I'll tell you about these basic things, what it means. If a function is continuous, okay, in closed interval a and b, this is the first condition. Second condition says that the function is differentiable, differentiable in open intervals a b. Then the third point is then there exists a point in between A and B. Now, one more condition is, okay, the third condition also is f of A is equals to f of B. Okay, so these are the three conditions. If there are 2 points, then think of it as 2 points, function value at point A and function value at point B, which is fb, function's value. This is point A, the function value at point A. This is point B, function value at point B. What it's saying is at point A, function value at point A, function value at point B, they are both equal. And given that there are two conditions which are also there, the function is continuous in between the closed interval, function is differentiable. What is meaning of these two things is I'll tell you. But is there anyone who can relate this to any natural life analogy? I just wanted to understand if we have studied calculus or we have understood calculus in somewhat form. Do you think whatever is coming out of these three assumptions, what natural life phenomena can you relate to these three things? Anything? Right. No. Gradient descent, no, no, not eventually. Bridge, kind of bridge, yes. Bridge, yes. Continuity. See, firstly, let me tell you about these two things. First, about continuous. Okay. Continuity means when I say a function is continuous in closed interval AB, it means that it includes those 2 points as well. It means that it needs to be continuous starting from point A. What I mean by continuous is you cannot suddenly jump from one place to another place. For example, this is continuous, but these two, let's say for example, that this is discontinuous. You have gaps in between. You cannot have gaps, something of this form. Continuity is you have continuous function without gap. You cannot directly jump from here to here, right? If there are sudden jumps from function, let's say this is point A, this is point B, and from point A to point B, this is how the function looks like, right? This is still continuous, okay? But there are other problems to it. This is continuous, but this is not differentiable. The second point says that the function has to be differentiable in open intervals AB. It means that there cannot be any sharp corners like this. Now, the problem with differentiable being attached to sharp corners is, remember I told you, differentiation is all about, let's say there is a function which looks like this. Differentiation is all about keeping it into pieces, making it extremely small, basically zooming into this entire piece such that at some point in time it becomes linear. If you have a sharp edge, okay, no matter how sharp, how close you get to, you will basically get a sharp edge, and that function with a sharp edge will never be linear. Now, because it will never be linear, hence all the linear assumptions that we make, all the linear studies that we make will all fail. So this is basically a convenient that we have placed for maths to work, right? Continuous says you cannot, when you sketch out a function, let's say this is how the function looks like, it cannot have gaps. Continuous is, it has to be continuous as the name, right? So it cannot have gaps in between. If you have gaps like this, sorry, if you have gaps like this, then the function is non-continuous, right? If you have situations like this, then the function is non-differentiable. Okay, so both of these things are important because the third point says that if you think about the third point, which is this functions point at A, function point, someone said that bridge, right? A function point at A, function point at B is all equal. If you think about it, this is FA, this is FB. Why it is important is because if the function is continuous, it is differentiable. Basically, there are no gaps in between, right? There are no edges in between. And then in that case, you know that there would be some point C where f dash C, where the slope is equals to 0. Think of now, think of you taking a ball and moving it, throwing it above in the sky. It will come back in the same height, right? You started from a point, the final position of the ball is on the ground. It started from the ground, came back to the ground, or basically started from your hand, came back to your hand, it reached a certain point wherein the slope was 0. So it reached a maximum point where the slope was 0. I told you last time that at maximas or minimas, there would always be slope 0, right? Think of a function which looks like this. Function's value at A, function's value at B, both are same, but there can be situations like this, right? So what Rolle's theorem is saying is there can be multiple points. There can be either one point C, or there can be multiple points at which the slope of the function is 0. And this is true, by the way, right? We already know last time when we were discussing about it. I already told you, right? If you look into a function which is like this, let's say for example, right? So herein, if you think about y and x, this is the range within x is changing. If you keep narrowing down this x range, right, in this at this particular place, let's say we are looking into this but smaller strip, right? X is changing from this point. Let's say this is point A to point B. X is changing. Y is the Y change, the change in Y, which is like say instantaneous rate in change. And then instantaneous change in Y, dy by dx would be almost zero because there is no change in Y at this point, right? It would be all flat. And that's what we call as slope is not changing, or the slope is constant, right, at that point. So this theorem tells you that if a function is having same value at two different points, okay, and the function is also continuous in between those points, the function is also differentiable between those points, then there exists at least one point C such that f dash C is equals to 0. This is good? Yes, no? Sorry, where it went. Yeah. I saw your question. How would the point it is, whether it is. That's why you have the assumption, right? So you are taking the closed interval, including the point. If you think about it, what we said, when we are saying the point A and B, right? This is point A, point B. We are saying that including these points, A, starting from this point to this point, it has to be continuous. It is not like the function was non-continuous up to this point, and then starting from this point it became continuous. We are not saying that. We are saying that including that point it has to be continuous. So it has to be continuous just before that as well. Okay, so continuous includes the closed interval. That's the reason why we are saying continuity between the closed interval. Differentiable between the open intervals, basically, but it's just saying that we don't include these points. It has to be differentiable everywhere else other than this point, these points. That should be fine, because what we're trying to say is we are trying to find out the point where the slope is almost zero, or the change in the slope is constant, it's zero. There is no, or the different rate of change of y with respect to x is almost constant, right? So we are trying to find out that those points, and we start evaluating from in between A to B, not exactly at A and B. It could, there could be chances that it was let's say, because we are looking into this entire thing, right? There are chances that it was non-differentiable exactly at these points, but we don't care about it. The only thing that we care about from optimization point of view is, are there any maximum points or are there any minimum points? That's what we want to know. We don't care about this point or this point, right? Good. Okay. Now, this is good. Let's say the ball analogy will help you understand basically, and this is so uh, so convenient to assume as well, right? You already know that when you throw a ball up above in the sky, it will attain a maximum height and then come back. So it will basically reach its maximum, and that's what we are trying to say here as well. So kind of someone who wrote that example of a bridge would attain a maximum height in between A to B, right? This is the height of the bridge. It will attain a maximum height wherein the slope is zero, wherein the derivative, the change in this value, whatever we are measuring, is exactly zero, right? So the derivative dy by dx, the instantaneous rate of change of the instantaneous rate of change of whatever we are observing here, and that bridge is with respect to x is almost equals to zero, right? So in that case, in those cases, it is It is all very intuitive to understand. But then people came ahead with the second problem, which is MVT, mean value theorem. Mean value theorem is same set of conditions. It says that the first condition, function has to be continuous, in between the closed interval a b, and function f has to be differentiable in open interval a b. So if we have a situation like that, okay, if it is continuous and differentiable within that interval, then it says that there exists a point C in between A and B. Then there exists a point C in between A and B such that f dash C is not equals to 0, but it is equals to fb minus fa by b minus a. And this is the most important thing uh, going forward in the lecture. You'll have to understand this well. So what exactly is the meaning of it? You have already understood what these two things are. Now what we are saying is we have removed the third condition. The third condition, if you remember in Rolle's theorem, was function's value at A is equals to function's value at B. We are saying that in MVT, this condition is not at all there. If this is not there, then we will have a point C such that the left hand side, if you think about the left hand side, what is left hand side? This is f dash c is instantaneous rate of change, something that on your motorbikes or on your cars, the speedometer tells you instantaneous speed, right? Instantaneous rate of change, right? On the right hand side, if you think of it, fb minus fa, let me help you understand the right hand side well. So think of you're taking a journey from, let's say, Delhi to Agra. Okay, let's say that it is 200 kilometers. I don't know. I've never been there, but let's say that it is 200 kilometers and it takes 2 hours. So on an average, if you think about your average speed would be 100 kilometers per hour, right? Because 200 by 2 is 200 kilometers per hour. That's what you are looking into. But eventually your speedometer shows you various different values. Your speedometer, while the entire journey is there, while you are on the journey, it shows you sometimes 80 kilometers, it shows you sometimes 120, sometimes 109, sometimes let's say 75 or even slower, right? So there could be a range of values that your speedometer tells you, right? So what Rolle's theorem says, what MVT says is, at some point in time, if you relate it to this example that I've given, the instantaneous change or the instantaneous velocity, the instantaneous speed that you have, which you see on your speedometer, right? On the left hand side is what you see on your speedometer. On your speedometer, you might see a value of 100. Okay, at some point. At some point, you might see a value of 100, which is exactly equals to your average speed. So right hand side is average speed. So what this theorem says is, it says that while we have, think of it as, if I draw it clearly, and they have people who made those slides, they have done really good work in demonstrating it. So think of it as, you have a function. This is function's value at A. This is function's value of B. See that they are not same. That's why this is being depicted like this, let's say. Now, if you think of both of them are not same, then you would have at some point the rate of change, let's say at here, the change f dash c at this point is equals to the difference between what is the function's value at b and what is the function's value at a, right? Fb minus fa divided by b minus a. So the instantaneous change at that point would be equals to the average rate of change. To help you understand this, I created it. I created this for all of us. Okay, think of this. This was your the first theorem. Okay, you are able to see exactly where the rate f dash c is equals to 0. There are 3 points. A and B, they are all f of A is equals to f of B. That's good, right? Even you can imagine various different places, there are various different functions. You will have different places. Right? This is what your Rolle's theorem was. Imagine anything, right? As long as f of A is equals to f of B, like the incident of throwing the ball above, you would have a situation like this. At least one point where the the rate of change with respect to the rate of change, instantaneous rate of change would be equals to 0. That's what is being shown here. Now, the second thing is if you have a situation like this, the function value is not equals to function value at the wherever you start from, where you end. If the function's value is different, in that case, you would have a situation like this. Sorry, let me create something or let me show it to you. Let's say that this is what you start from here, you end up here. Now, if you look here, the function's value at these points is equals to the rate of change. This dashed line, secant line that you see, that is the average line, right? So f dash c would be equals to fb minus fa by b minus a. That's what is being shown here. Okay, and you can change it at various different places. So basically this white line is parallel to this dashed line that you see of average speed. Okay, this is, think of it as you are starting from this point. Let me stop it, pause it. Think of it as you are starting from this point. You took some up and down travel, right? Sometimes the speed was low, sometimes you are accelerating, sometimes you are not accelerating, right? But on an average, in between A to B, this dash line shows you the average speed. Now, this average speed, when you are calculating average speed, at some point in time while in your journey, your instantaneous speed that you are seeing on your speedometer would have been equal to the average speed. That's what is the meaning of mean value theorem. But the idea of mean value theorem is much more bigger than this. Okay. Why I'm saying this is because if you think of what we have written, f dash c is equals to fb minus fa divided by b minus a, right? If you rearrange it, you would be able to see fb is equals to f of a plus f dash c into b minus a. This is what it would eventually come. Both the things are same. Whatever you saw it, basically this is your mean value theorem. But if we rearrange and write it in terms of fb is equals to, you will eventually get to this form, right? Now, what this tells you? So it tells you that function's value at a new point B. Think of it as you started from A. Okay. A function's value at a new point B is equals to what you know about the function's value at A, right? You already know what the function's value is at A. So to know the function's value at B, a new point, it is basically equal to, it can be easily approximated using the function's value at A plus you know that you know a point, or let's say let me re-change it, how the slope, how the basic f dash c is nothing but the rate of change, right? How the slope changes between b to a. So it tells you to estimate the function's value at a new point b. If you already know the function's value at a given point a, what you need to do is you just need to add the function value at a plus how does the function behaves around or in between b to a, right? What is this, how does the slope changes between b to a? That's what it means. But think of it again, the problem is we don't know. If you think of this situation, right, you don't know where that c is, whether this c is here. If you know the graph, right? If you know the graph well, you will know where those C's. But those C points are very difficult to get to. Okay. If we don't know C, if we don't know where exactly is that point C, then approximating, let's say, using it here is difficult. So what we can do is think of it as, again, let's say that you start from this point A. Okay. If you are very near, and this is the new point B. Okay. Then you can just say that function's value of B is approximately equals to function's value of at A, right? So the idea is, if if you are very close to point A, then the function's value at the new point would be very close to function's value at that point, right? Or you can also say that function's value at new point B, or the rate of change of function's value at the new point B, it would be almost equals to function's value at. Same logic goes in, and it says that if C is very near to A, that the C point, which is very near to A, in that case, f dash C would be approximately equals to f dash A, right? Because the C point is very near to A. So you can approximate whatever the rate of change or the slope at C would be the rate of change at A as well, because the points are very close by. Think of, I'm just helping you understand. Think of a sine wave curve. Okay, this is how it looks like. If you think of at this point 0 or a point 0.5, right, or let's say 0.01, in that close proximity, the slope is almost same, unless and until you go here in where it starts changing. The slope between these 2 points, that is almost same, right? So if you are evaluating the function in between these 2 points, if you are trying to approximate function's value, let's say this A, this is B. If you are trying to approximate function's value at B and you know that the function value at A, then you can just simply write function's value at B is equals to function's value at A, right? But there should be some change, some slope change which might be happening. Hence, you can also write using the same Rolle's theorem. You can also write which is equals to B minus A into f dash C. Now we can say f dash C if the point is closure, and you can approximate with f dash A. So FB is equals to FA plus B minus A into f dash A. Right. Now this is much better approximation. It says that function's value at a new point is equals to function's value at where you know the function's value. Okay. And how the slope changes around that point, around that point A. So first, how far is B from A, and how the slope changes around that point A. Because if you think of, if the function is changing abruptly, this is A, this is B, then you will have to approximate the function's value at B. Firstly, you add what is the function value at A, and then you see how does the functions, how does the slope changes around this region, right? That's why you take into account B minus A and what is the rate of change of function at A. So that's the idea. Idea is to approximate the function's value at a new point. You add what is the function value at a known point, and then keep. I mean, I'll get to this second part. See how the slope changes, how the function changes around that point, and then keep doing that. Now, this idea is simple. Think of it as, if you have to, I mean, just in simple sense, if you have to uh, let's say recreate a, a new organism. If you have a DNA, okay, from DNA you can create the entire embryo, or let's say whatever it is. Then you can create the entire specimen, whatever, right? And then you can create the entire individual. So from DNA, you just need to know one single point. From that, you can actually develop the entire individual. The idea is, if you think of, the idea is this. If you look here, this is the intuition for Taylor series, okay, using the function. So think of it as, when you are exactly at point A, let's say you know what is the function value at this point. Okay. Now, if you want to know the function value at a nearby point, somewhere nearer, okay, you might want to approximate, let's say if the function is here and the new point is here, b is here, or let's say the b is here, using this single line, okay, using only one variable, 1 degree function, you will not be able to estimate the function's value at a new point. You will need few more terms. For example, how does the function changes at, or how does the rate of the change of the function looks like at that point, right? Which is what you saw there. If you think of what you are saying is fb is equals to fa plus b minus a into f dash a. So basically what you're saying is, if you have to look into a new point b, it can be approximated using what you know about a. Then what is the rate of change of the function at a, right? F dash a. So if you know both of these things, it is easier to approximate. But think of it. If you go, let's say the sine curve that you're seeing, if you have to approximate the value here, you already know the value at this point. This is your a. Now you cannot only use these two to approximate, because what it tells you the f dash value, f dash x would look like, the tangent would look like this, right? Using this approximation plus the value at this function, you cannot approximate the value at this point. This point is b. What you would also need is, how does the slope itself changes. The slope is not constant. Let's say, for example, let me redraw it to help you understand that. So think of it, this is your sine wave function, right? At this point the slope might be constants, but here it is changing. Every point slope is changing, right? Here it is this, here it is this. So every point slope is changing. So you would have to add new terms to this entire equation to approximate function's value at b, which would be higher order function. So basically you'll have to derivate this now. So derivation of the rate of change of the function at a would be double derivative of a, which would be like this: b minus a whole square by 2 factorial into f double dash a. If you continue this thing, actually, if you continue this thing, this entire intuition, you can write it as, let's say you started from b minus a to the power 1 f dash a divided by 1 factorial. Then you have b minus a whole square f double dash a divided by 2 factorial, right? Then you will, if you continue this, it can go up to like this: b minus a whole cube f triple dash a divided by 3 factorial, plus and so on. You can write it as b minus a whole to the power n f triple dash a f, sorry, fn, let's say, n times derivative, okay, divided by n factorial. This is what it would be eventually with n terms, right? And you can actually write it up to infinity as well. So what it says is, to approximate a function around a new point b, or at a new point b, you start with simple approximation. What is the value of the function at a? But as b, if you think of, this, if the point b is here, you can easily approximate. Let's say this is the point b. But if the point b is here, you can approximate using fa plus how does the rate changes, right? You can approximate using these two terms easily. But if you go to this point, you will have to also understand how does the slope changes. So you'll have to add the third term, or the third variable, sorry, the third term here as well. Then if you have to maybe go more far away from point A, then you'll have to add the fourth term as well, and so on. And this is the intuition which I was showing you on that HTML. See here, this is the first term, this is the first term. Okay, simple approximation up to, it will only work from if your B is up to here till here, right? If your B is somewhere here, this entire approximation with 2 will not work. Then you'll have to add more degrees, right? 2 degree functions, you will have to add 3 degree functions, 4-degree functions, 5-degree functions. And then if you keep adding more and more, you can approximate the entire sine curve. That's the idea. Okay. So this is the intuition for, and the Taylor series is basically originating from mean value theorem. The idea for Taylor series originated from mean value theorem, right? So this is that simple idea. Or you can look into cos functions as well. You look into e to the power x. You can look into log of x, or 1 by 1 plus x. Now Taylor series is important again, and just give me 10 more minutes, and then I'll come back to all of you for questions. Taylor series is important because uh, this is good way of approximating functions, approximating values of functions. Now, if your functions are like x cube plus 4x square minus 5x, the polynomial functions like this, it's easier. But think of if your function is e to the power sine log of x plus 1. It's pretty tricky enough, right? And when you didn't had calculator in 17th, 18th century, when Leibniz and Newton, all of these guys were doing these calculus things, right? It was extremely difficult for them to, they didn't had calculator to find out, put in the value of x as, let's say, what 10 and so on, and get to what exactly would be the value of the function at that point. They can do it today, but back then there was no calculator. Okay. Now, calculator eventually invented using this entire logic approximation. I mean, even in 19th century, if you will go back to history, the Taylor series gave back to the idea of finding out values of these functions are called as, let's say, sine x, cos x, log of x. Okay, these functions are, or let's say all of these types of functions, these types of functions are called as uh, non-polynomial functions, right? So all of these non-polynomial functions, non-polynomial, polynomial. If you have to find the approximations for a non-polynomial function, and right now we have a lookup table saying that sine 30 degrees is equals to what, 1 by 2 or whatever, right? Now let's say sine 90 degrees is equals to 1, or so and so on. You already know that what is the value of the function, because you have certain values that we have memorized. But if the computer has to calculate it, how would it calculate? So how would it calculate back then in 19th century? Think of it. The idea was to convert these non-polynomial functions into polynomial uh, fragments. For example, e to the power x is written down as 1 plus x by 1 factorial plus x square by 2 factorial plus and so on up to infinity. So this entire series originated basically because of Taylor series. Okay. And this series is saying to approximate e to the power, let's say e to the power 0.1, what you need is you just feed in x equals 0.1. Let's say 0.1 whole square by 2 factorial plus and so on, right? That's how simple it is. If you keep adding more and more terms, more closer to real value you will be getting to, right? If you just approximate using two terms, you will not have a very good approximation. Uh, the the intuition, or let's say the simple intuition that I can tell you is, imagine you are trying to copy a signature. Okay, if you are trying to copy a signature, the level 0 of that would be match the starting point, the start point. So let's say, for example, let's say that this is the signature that you're copying. You'll first match where it all started with, right? This is what, let's say, you have to write down. You will, where it started. This is the point where it started. Then that's the first thing, right? Level 0 is match the start point. Level 1 would be, then the next approximation would be, if you have to approximate someone's signature. I know most of us might have done it at some point in life, right? So the second level of approximation would be match the starting point plus direction where it moves, right? So let's say you start from here, then how it curves, how it moves. So direction. This is why you add f dash a. This starting point is what your f of a is. Then level 2 is match the starting point plus directions plus bend, right? Now this higher order terms f double dash a, these terms are basically finding out how does the function curves. So that is where it is important. Then level 3 would be basically adding all of these things that you have done up to bend, plus how the bend itself changes, right? So on and so on and so on. So this is how you approximate any signature. This is how you do it. I mean, simple real life analogy is that. And that's what you are doing here as well. Okay. Now, to help you understand where this formula came in from, just give me 5 more minutes. I'll come back to all the questions. So if you think of where this formula came from, think of you have a function fx is equals to e to the power x, right? And you would want to know, let's say the question is approximate e to the power 0.1. Okay, you don't know anything about it. You also don't know the e to the power x has a long series, which is 1 plus x by 1 factorial plus x square by 2 factorial plus and so on. You don't know this as well. Okay, now how would you approximate it? So the very first thing is you already know that function's value at a new point b is equals to f of a plus b minus a f dash a plus b minus a whole square by 2 factorial f double dash a plus and so on. You already know this, right? So let's say b is that new point, which is, let's say in this particular case, it is x. So you can write, let's say f of x is equals to f of a, okay, plus, and you already know that e to the power 0 is equals to 1. So you already know function's value at at a, which basically a is equals to 0 in this case, right? You already know e to the power 0 is equals to 1. You already know the function's value at a is equals to 0. So let's say, let's put it a as 0, f of 0 plus it would be, like, because b is x here, so you will have x into f dash 0 plus x square by 2 factorial into f double dash 0 plus and so on, right? Now you can write it as fx is equals to f of 0 is what? E to the power 0, e to the power 0 is 1, right? This would become f dash. So if you think of e to the power x, its derivative f dash x would be e to the power x itself, which would be eventually e to the power 0, which is 1. So this also becomes 1. So x into 1, then x square by 2 factorial. This also becomes 1 if you think of, because it would always be e to the power x. So this also becomes 1 plus and so on. So eventually the entire series becomes 1 plus x square by 2 factorial plus and so on. So all of these series that you see, whether it is e to the power x is equals to what? Sine x is equals to x minus x cube by 3 factorial plus x to the power 5 by 5 factorial minus x to the power 7 by 7 factorial and plus and so on. All of these series, this series, or what we saw as e to the power x here, right? All of these series are created using Taylor series. Okay, because idea is you already know what is the value of the function at a point, which is e to the power 0. You already know that sine 0 is equals to 0. So you can approximate it at nearby point using Taylor series. That's the idea. Okay, that's why there is Taylor series. Now I will go back to two-dimensional Taylor series and will tell you about what kind of problems are going to be asked in your exam. But let me get to your questions first. What is the joke about? Yes, exactly. The idea is more variables, more closer to the. Any questions?
So I have a question.
Yeah, go ahead.
We are reading about all this Rolle's theorem and MBT and Taylor series. How do we actually use it? And where do we actually
Good,
use it?
good point. Good point. You have studied gradient descent, right? What gradient descent tells you? W new, the weight parameters, the new weights basically is W old minus step size into the gradient of the loss function. That's what you know, right? And what does Taylor series tells you? Function's value at the new point is equals to function's value at the old point plus uh, b minus a, or let's say actually b minus a, let's say that the step, and b minus a is how far b is from a, which is step, into f dash a. Now these two things are exactly same, because if you have a variable of multiple dimensions, or let's say function of multiple variables, then you take get derivatives, sorry, gradients. Okay, here we are dealing with one dimensional function, only x, right? Function of x or function of y. Hence we are writing it as this. But what the idea of gradient descent has been derived from Taylor series itself, because what we are saying is new value of the weights is equals to old value. Now you might ask, where does this negative sign comes from? Negative sign comes from basically because when we take gradient, let's say for example this function would have been a multi variable function, okay, then we would have taken gradient and we would have written Taylor series like this: fb is equals to f of a plus uh, plus h times the gradient of function. Okay, this is what the Taylor series would have looked like. But if you think of it, the gradient of the function is tells you increase in the function's value. We want to do gradient descent, not ascent. Hence, we take negative of gradient ascent. So this entire formula is this. So there is a small tweak between what Taylor series tells you. It's just that we don't want to achieve the highest point. If you start from somewhere, you are not trekking to go to the Mount Everest. You are trekking to reach the minimum most point, because in machine learning, you want to minimize the loss which your loss function is making, right? You want to be as accurate, as close to the real value as possible. So you want to go gradient, do a gradient descent rather than gradient ascent, hence this negative value. Now why MVT has been told to you? Because this entire idea of FB is equals to f of a plus b minus a times f dash a, it basically came from the same idea, right? Which is which tells you f dash c is equals to b minus a, sorry, fb minus fa by b minus a. So from here we move to Taylor series. From Taylor series we move to gradient descent. That's why. Good.
Yeah, okay. Thank you, sir.
And there are multiple ways in which you can actually study about them, study about Taylor series, various different. Uh, just a minute. Okay, so there are multiple ways in which you can, in multiple blogs, you will see that they have described Taylor series in different ways. But the idea basically is very simple. I mean, you start from what you know, keep adding what you could know, based on how the things changes from what you know, right? If you have to uh, get to a new destination, firstly you would start from some point and then change basis based on what you keep learning as you go along, right? So the idea is that, but this entire thing is not, I mean, from machine learning point of view, it is not only gradient descent. Think of approximating, you have already known. uh, Now you need to elevate your thinking in terms of, because Taylor series is an approximation method, right? And if you don't know the function, around a particular point, you can use Taylor series to approximate the function. So there could be various different ways in which Taylor series could be used. One of the ways is gradient descent, but then there are multiple ways. Let's say you might have learned about Newton-Raphson, Newton's method, right? And all of those things are numerical methods for approximating functions. But Taylor series is itself is a so profound way of approximating functions without even just you need to know one point. If you know one point, you can actually see here, you can actually cover the entire function. You can actually learn the entire function just by adding up more and more parts to it, right? More and more terms to the equation. That's the idea. But the kind of questions, after that, I'll go to Hessian matrix. The kind of questions that are going to be asked in your exam, they'll not be one variable questions. Okay. They will be questions on two variables like these. So if your idea of Taylor series is, if you think of, let's say, just a minute. If you think of, I have just told you f of b is equals to f of a plus b minus a into f dash a plus b minus a whole square by 2 factorial f double dash a plus and so on. Okay. Now, if you think of, let's say that let's say that you would want to know, you already know the function's value at a point A. Now you would want to know the function's value at a point X. Okay, such that whatever the distance that you have h, which is the difference between x and a, so you can write h is equals to x minus a, or you can write as x is equals to a plus h. So basically what we are saying is when you know the function's value at a point A, okay, and you move h distance away from it, which is basically the new point x, now you are trying to approximate function's value at a new point x. So you can change this entire series, the equation that I wrote above, as f of x, the new point, is equals to what you know at fa plus, let's say, because b is the new point, right, which is your x minus a. So basically this would become x minus a. This entire thing would become x minus a, right? So x minus a is nothing but h. So it would become h into f dash a plus h square by 2 factorial into f double dash a plus and so on. Now this is one variable. You can actually add the same intuition and add it a two variable function. So let's say functions, if a function, if f is a function of two variables x and y, so f is a function of two variables x and y, and you would want to know the function's value at a new 2 points x and y, any new points. Okay, so let's say you already know the function value at point a and b, so you would just be writing what is the function value at a b, because you have two variables now, plus the second term, which would be uh, f. You can write, let's say, fx as the partial derivative of the function with respect to x. This is right, partial derivative of function f with respect to x, fx, or you can write h here because this h is multiplied there as well, right? Fx at ab. Okay, then you can write k. K is basically just as you are writing h is equals to x minus a, you can write k is equals to y minus b. So basically how far you are moving from your known point b in y direction. Okay, and hence you will be writing k into f of y a b. Okay, so this is your this term is your linear approximation of the second term. Okay, then you will be having 1 by 2 factorial, and then you can write double derivative. Basically f double dash would be fxx, double derivative of with respect to x, and you would be having AB. Here we will be having H square, right? Plus K square FYY AB, right? Plus you would have, basically you would have H and K. Basically you would have cross derivatives as well. First derivate the function with respect to x, then derivate the function with respect to y. So you'll have x fxy a b, right? And the terms would be hk. Think of it as this entire term. This is what you'll eventually get to. No one is going to ask you questions on third degree term and so on. If they ask you the questions, if you have to memorize it, think of it as a plus b whole square. Formula is a square plus b square plus 2ab, right? So this is that ab term which comes in. I mean, I'm not saying that you have to memorize it in this way, but I'm just saying that how does this, the first is intuition wise, first is double derivative in x direction, double derivative in y direction. But if you think about x and y, it's not only derivative in terms of x direction or y direction. There could be derivative, the rate of change in combined direction as well, right? If you have a function which looks like this entire function, right? Let's say you are not measuring the change with respect to this direction or this direction alone. You are also measuring the change with respect to x and y direction as well, right? So you will have to add fxy as well, which would be the value of the function at AB. So how does the function or the slope of the function changes in this direction around the point AB? So you have three different terms to be known from your exam point of view. First, there are 99% chances are there. They'll give you the two variable function, something like let me solve a problem on this so that you can understand that how can you do that, and it would be easier for you to actually understand it better. Okay, so let me first tell you to know the function at a new point. Let's say the function is a two variable function. To know the function value at a new point, first function value at AB, what you already know, plus the function's value or the rate of change of the function in x direction. Okay, the rate of the change of the function in y direction. Okay, then you have double derivative, the rate of the change of the slope in x direction, the rate of change of slope in y direction, the rate of change of slope in xy direction. That's what it is. Don't forget to add these factorial values as you keep adding more terms. Okay, but eventually you will not get more than 2 degree to add this 1 by 2 factor. Let's solve a problem so that you understand all of these things well, and it would be easier for you to actually get an idea or intuition about it. Okay, so let's say that you have, let me imagine a function. Let's say that you have a function fxy is equals to x square plus 3xy plus 2y square. Okay, let's say that this is the function that you have. Now, let's say you already know um, a and b. Let's a is equals to 1 and b is equals to 2. These are the 2 points that you already know the function's value at a, or let's say function at 1, 2 is what you already know. Okay, the function's value at 1, x is equals to a and y is equals to b. This is what you already know, for example. Okay, because if you will feed in 1 2, you will eventually would get to know what is the value of the function at that point, right? Now we have to find out what is the value of the function at any arbitrary point xy. That's what we'll have to find out, let's say. And then they might also give you that xy point is something, right? So they might give you the new point values as well. So let's first look into how can we solve these types of problem. And there are very uh, it's very obvious that you might get a question like this in your exam. Okay, so the very first thing is you will have to find out. Remember, I told you h and k values, right? H would is nothing but x minus a, and k is nothing but y minus b. So a and b you already know. A is 1, b is 2, so it would become x minus 1, it would become y minus 2, right? So now you have to find out the function value at the very first thing is fxy is equals to f of ab first, then the higher order terms, right? And so on. So first let's find out what is f of ab. So f of 1, 2, for example, would be f of 1, 2 would be just feed in x is equals to 1, y is equals to 2. It would become 1 square plus 3 into 1 into 2 plus 2 into 2 square, right? Which would eventually come down as 1 plus 6 plus 8, which is basically 15. So the very first term is 15. You are good with this is the approximation of, or let's say the very first term value is 15, which is good. Now the next term, which is the higher order term, the first derivative terms, fx. You have to calculate fx and you have to calculate fy. Okay, what is fx? What is the partial derivative with respect to x for this function? What is fx? Partial derivative of the function with respect to x. Am I audible? Yes, no.
2x plus 3y.
2x plus 3y, right? 2x plus 3y. So, and then fy would be?
3x plus 4y.
3x
Yes, 3x plus 4y.
Right, 3x plus 4y. Now, you, for the second term, if you think of, the second term is fx at ab.
Sir, these fx and fy will be f dash x and f dash y.
There, this is the way of writing it. What we, when we write Taylor's series, fx is basically the uh, first order derivative of function f with respect to x. We write it like this. Okay.
Sir, fy equal to 3x plus 4y.
3x plus 4y. Okay, sorry. Right. That should be 3x, this one, and 4y. Yes. Right. Now what you need to do is to substitute it, you first need fx at AB and fy at AB. Fx at AB, so at AB, 2x is equals to 1, y is equals to b. What is the value of the fun? So basically we are now finding out fx at AB, which is fx at 1, 2. What would the value of that? 1 plus 3, right? Sorry, 1 plus 6. It would be 8, right? 1, 2 into 1 plus 3 into 2, that is 8, right? And then similarly, you will calculate fy 1, 2. It would be 3 into 1 plus 4 into 2, 8 plus 3, 3 11. Plus. Yeah, right, exactly 11. Right. So now you have all the things needed. H is what you already know, right? It would be basically x minus a. So the output would be, so basically if you have to write out, you have already known 15 plus h into, let's write h like that. fx 1, 2 you already know, right? Which is 8 plus fy, which is 11k, right? And then this is the first order derivative. Then you will be adding the second order derivative 1 by 2 factorial. What would be the second order derivative of this function? You have already found fx. You just derivate it one more times with respect to x.
2.
Right? fxx would be 2. Then you will write fxy. What is fxy?
4.
3.
4.
3.
3, right? And fyy 4, right? That's what it would be. So basically you have found out these three terms, these three values as well. So you have found out these three values. Now these are independent of x and y. So you don't have to worry about it, right? So you just directly can feed in fxxab. So the value basically would be 1 by 2 factorial. If you think about, it would be 2 into h square, right? Because the first value is 2 2 into h square plus what it would be 4 into k square, because the last value is 4, and then 2 into 3 into hk, right? This is what, so this is your expansion. This is what eventually would be asked. So this is the kind of thing that you'll be doing right now. You already know what is the value of, let's say, if f of xy, this is f of xy. You already know x is what? X is, remember, x is equals to h is equals to x minus a, hence x is equals to a plus h, right? Or 1 plus h, you can. So you have f of 1 plus h and 2 plus k. This is that expansion. Okay, around, let's say, h unit away from 1, k unit away from 2. This is that approximation of the function. Okay.
So how we calculate f of x, y? Can you explain once? F of x, y.
F of xy. You have
Even
this
sir,
term.
f of xx and f of yy also.
Mhm. See, herein you have this term, right?
Oh,
F of xy,
oh.
right? So whatever you do, firstly with respect to y, if you derivate this, think of it as if you derivate it firstly with respect to x, right? So in that case, what would it would be 2x plus 3y. Then you will derivate it with respect to y. In that case, this would become 0. You would only be having 3, right? If you think of it as your function is x square plus 3xy plus 2y square, x square 3 plus 3x square, sorry, 3xy, 3xy plus y square. Okay. Firstly, fx is simple with respect to x, right? This would become 2x, right? This would become 0, right? This would become 3xy, y would become constant, so 3y into, so this would become 3y. Just I don't know whose voice is that. I would do, but anyways. So this is what fx is. Fy is derivative of this entire thing with respect to y. So x square would be 0 because it's constant, right? This would become 3x because y to the power 1, it would be 1. So whatever is constant would only be remaining. Then you would have 2y. This is what you have. Now, either you derivate this to find out fxy, either you derivate fx what you have found out with respect to y. So if you derivate this entire thing with respect to y, this would become 0. There would be only 3. Hence, fxy is equals to 3. Or else you have already find out fy, right? You derivate it with respect to x. So this would become 0. Hence, whatever you have is 3. In both the ways, fxy would always be 3. Now from here, whatever you have got as fx, which is 2x plus 3y, if I have to again derivate it with respect to x, then fxx, which is the double derivative, it would be, because this term is independent of x, this would become 0. 2x would become 2, right? So you have 2. Fyy, if you derivate, let's say fy is this one, right? If you derivate it with respect to y again, this would become 0 because it's independent of y. Only this term would remain, which is 2. Then you have fxy derivative, which you already know, which is 3, right? So that's what it was. If I have done it right, I don't know what I took. Actually, it's what 2y square. I took it as y square. That's why I found that fy is coming as 2, not 4. But anyways, if you have this function, this is how it would look like. So eventually, everything is basically finding out the right derivatives. If you practice it well, you are going to do it well. Otherwise, it would be a problem. But practice these types of problems. I mean, I'm just saying that.
Hello, sir. Sir, just repeat the problem once again. Means we understood all the derivatives, but just from starting, what was the equation that fxy was that x
Okay.
square plus yes. And what was the requirement? What was the required from our side? What was the question actually?
Question would be, the questions would be, given the value of the function at a point, at a known point, okay, they will give you, let's say that you have to find out expansion of, let's say there is a function fxy, okay, and they might give you a function like x square minus 4xy plus 2xy, or let's say 2y plus 3x. Okay, this is a big function. And the idea is simple. You know what that function is in terms of x and y. They might ask you, what is the expansion of the function? The question would be, how does the expansion of the function looks like around point 1 and 2? Okay, that's what they will be asking. Around point meaning 1 plus h and 2 plus k. Some distance away from 1, some distance away from 2. That's what you will have to find out. Okay, f of 1 plus h, f of 2 plus k. So how much we can approximate, or what would be the approximated value of the function h units from x, k unit from y, okay, or from the known point 1 from 1 and from 2. So they will give you to expand it at exactly at that point. This is one of the types of questions that I have been seeing all across. I'm not saying that the only type of question that can be framed is only this from Taylor series, and it is almost sure that it will be asked. So it's better that you practice it, because they will give you a function like this, and then they will give you to expand it around a point. So to expand it around a point, you will have to write it like this way: f1 plus h2 plus k, and this is basically nothing but f function's value, let's say, at ab, right, which is 1 2, function's value at 1 2 plus um, h into fx, right, at 1 2 plus k into fy at 1 2 plus 1 by 2 factorial, all those terms, right? H square fxx around 1 2 plus k square fyy at 1 2 plus hk fxy at 1 2. So this is what you'll have to find out, all of these partial derivatives, because what it says is h units away from 1 and k units away from 2, both of those known points at which you know the function's value, and this is how it would expand. That is what they are going to ask you. They will give you the the equation, sorry, the function, and they will ask you to expand it around a particular point. That's all.
So we have to remember this in the bracket, what that fxx, fyy, that bracket, that equation we
You
have
have
to
to remember
remember.
this. Yeah, you have to remember this.
So
Sir,
this
I
is the
have
tough
one
part.
question.
Mhm.
Hello, sir.
Yeah, yeah, go ahead.
I have one question. Like you always say, I may be missing previous lectures or somewhere. You always say that I will be giving problem, but I don't see. Maybe I'm missing in Taxila. I cannot see any problems given for solution or to do something. Is it given somewhere else?
No, it is given on Teams. I am so sorry if you have had the problem, but if you go to Teams, and this is what your mathematical foundations, right? So which one it is? This one. So sorry, not this one, I think. Yeah, this one. So if you will go to my section and then on shared, you have all of these lecture documents for everyone. Okay. So for
Okay.
example, for the last lecture, I have it a practice set. So you'll have it here on Teams. Similarly, I have added, for example, for this lecture, I have added the component doc, but I will add this component again. Going by this component doc might make life easier for you, because
Okay.
if you'll go through this, it has only few pages that you need to know. from ML point of view plus from intuition point of view. All the examples that I gave you is actually
Yeah,
here.
thank you, sir. Thank you very much.
Okay.
Okay.
And this is that entire part. If you remember this part, let's say if you remember this entire thing, you are good from your exam point of view.
Okay. Yeah.
Sir,
Okay.
give us some solved examples also.
Yeah, I'll give it to you.
Sir,
That's not
one question.
yeah.
Yeah, so in this question, after differentiating 2 times, it becomes constant, we are good. If it doesn't become a constant, do we do for 1/3 factorial also? Or do we stop
No,
there?
I think see the thing is it's a 2 hours problem, 2 hours paper, right? So you eventually hardly have 15 minutes. If this question is going to be asked, it will. This is my intuition. This question is going to be asked. This will not be asked as one complete question. This would be a part of the calculus problems. Okay. If it is a part of a calculus problem, they can only give you, obviously, to write third degree polynomial, it will take somewhere around 15 minutes to just to derivate and cross check it, right? So they will not give you a question which can be solved in 30 minutes. So be assured that the only type of problems that they can give you would be restricted to x square, or let's say maximum degree would be square 2, right? Whatever it is, xy. They can give you some fancy terms like, let's say, log of x y, something like this, but they can never give you something which is more than x square, or let's say x cube and so on. In that case, you'll have to go ahead and do um, more derivatives, go to third term. Even if they give you something like this, for example, just I'm giving you an example. Let's say even if they give you something like this, x square plus 3x square plus 4xy. Okay, this is a simple function. If they give you, and they will not ask you for the third degree expansion. They will only ask you for second degree expansion till that point. So even if your function is free of, let's say, ffxx is not free of, in this particular case, it will never be free of x, right? It will be not a constant. Mostly it would be 3 to 6x, right? So because it would be 6x, so you just write it as 6x. That's all. That won't be a problem. Okay.
Sir, if I may ask one question, there were discussions around calculator. First thing is it allowed, and if yes, which one?
I think it is. I don't remember the one which I shared in one of the WhatsApp groups. There's one which I shared. I don't. I think your teammates.
It is FX equivalence.
Okay, thank you.
Yeah, that is the one that will be used. But again, people who have been discussing about calculators, there are two things that you need to keep in your mind. First, the kind of problem that I have been seeing in all these years, it's not you are given problem to calculate. The problems would be more tricky problems wherein you would be involved in the thought process more. I mean, not tricky, I would say that the problems are straightforward, but they are not calculative in sense. Let's say the calculation would only come in when you are doing maybe uh, mm, bigger multiplications, but I have never seen something that cannot be solved by hand. Okay, so it doesn't matter whether you have a calculator or not. I have not seen, other than if there are problems on SVD, which are very rare, and if there are problems on SVD, then also it will not take huge amount of time for you to do those calculations. Okay, so the dependency on calculators is hardly less than 5 minutes in the entire scope of 2 hours of exam. Okay, so it all depends
Sir,
on
so
how.
can we leave, yes, can we leave fractions like say 1/√2 kind of things as is, or do
Definitely,
we need to?
definitely,
Okay,
definitely.
then we don't need calculator at all. Okay.
You don't have to fully completely solve it. Because your question is very right, because mostly what would happen is you will get to a state wherein when normalizing a vector you will get to 1 by root 2 or 1 by root 5 and so on. Just leave it there. Don't have to do more, spend more time. Again, telling you, there are, the way this entire question paper is devised, there would be 6 7 problems. 6 7 problems with multiple choices itself basically gives you a very narrow window of 7 10 minutes of time, maximum 15 minutes of time for a long question or larger part, right? So in that, if you are going to do all of these things, it will basically take up your time. So utilize your time well. Do not give any question more than 10 15 minutes. It will eventually end up, you will end up not solving most parts of the questions. And go through, if you practice calculus well, all the things that I have taught till now, partial derivatives, gradient descent, Taylor series, these are sure short questions. Practice them well. I mean, the only pain point is calculating the derivatives. If you are good with derivatives, it is going to be very easy thing for you. Okay.
Quick question here.
Yes,
Here
yes.
we discussed about plus x value for both h plus and k plus. Can it be also possible they are asking about a minus concept?
It is it
And how
is
does it change the equation? Like if we take a minus.
it is same thing. If you think of, we are saying A plus H and B plus K. A and B could be any points. Okay. Now, if H is some, wherever, whichever direction you are moving, either positive direction or negative direction, basically, let's say A is 1 and H is minus 2. So in that case, it would be minus 1, right? B is 2 and K is, let's say, minus 3. So in that case, it would be minus 1. So you are evaluating at minus 1 1. So all all combinations are possible based on whatever value you can assume for H and K. Okay. We are
Sir,
not.
one last question, sir.
Go ahead, go ahead.
What will be the partition between linear algebra topic and this calculus part in the marks weightage?
This is how it is going to be. Actually, eventually, what it would be is, I'm not sure about it, but this is, I'm just saying that there would be, let's say, 1 to 6, topic 1 to 6, and then, sorry, 1 to 5, and then 6 7 8. This is all your vector calculus, right? This is all your linear algebra. Now, more weightage would be given to this. For example, 25, sorry, this is 30 marks question paper, right? Sorry. So because this is 30 marks question paper, you can imagine, let's say, 18 to 22 marks coming from this part, and same, let's say, 12 to 10 coming from this part, or let's say, for example, 12 to 8 to 12 marks coming from this part. Okay, so that's what it would be. So mostly 70% from this side and maybe 30% from this side. This is what it would be. But eventually, I'm just saying that in this side, the questions are not going to change. There would be questions on gradient, there would be questions on partial derivatives, there would be questions on chain rule. There could be, I'm just saying that because going through the the question papers in last 2 3 years of time, that is the idea that I have got to, right? So you can practice more, practice. If you are good in derivatives and if you are good in calculus, or you have got the idea of calculus, practice more from here. This is actually the scoring side of it. They can bend questions in various tricky ways in these sections. This is not a scoring area. I'm just saying that if you're good in here, I am pretty sure you will score good. But if you're not good in here, this is the place wherein your intuition, your thoughts, everything would be tested. So this is the place wherein majorly you will lose your marks, but this is the place where you will gain your marks. I'm just giving you my idea of how it should be, how you can.
Okay, I got it. Thank you. We can continue.
Okay. So now, if you think of this part, Okay, this particular part, what it says, if I have to write it here, 1 by 2 factorial, and let me write it cleanly. H square f double derivative of with respect to x at a particular point, let's say that particular point is known, let's say AB, plus k square double derivative of the function with respect to y at point AB, okay, plus hk, the joint derivative, or let's say with respect to x and with respect to y, with respect to at point AB, okay. If you
The
see
two
this,
is there, you missed 2 times of h,
yeah,
2hk.
right. This, yeah, right. 2hk, right, exactly. So this is what it is. Now, if you think of these three terms that you have, fxx, fxy, and fyy, these basically constitute a special matrix. These are the constituent terms of a special matrix, and that special matrix is called as Hessian matrix. Okay, think of it as you have gradient as a assembly of partial derivatives, right? So let's say there is a function which is a function of two variables x and y, then you will calculate that the derivative with respect to x, the derivative with respect to y. This is partial derivatives, right? Or you can write it as like this as well, df by dx, df del f by del y, actually del f by del y. It's basically the same thing, right? This is the gradient. Gradient is first order derivative of the function with respect to the two variables that you have, one with respect to x, one with respect to y. That's what is gradient. Gradient tells you the direction, okay, and of steepest ascent, and I'll come to why this is called as steepest ascent, but gradient tells you that, right? Hessian is think of gradient again, think of gradient as, because this is instantaneous rate of change, right? When you take dy by dx, it's an instantaneous rate of change. Basically, this is the instantaneous rate of change of the function with respect to x, instantaneous rate of change of the function with respect to y. This is basically what your speedometer tells you, right? Now, Hessian is a matrix of the double derivatives of the function. So you will have functions double derivative with respect to x, functions derivative with respect to x and y, functions derivative with respect to x and y, and function derivative with respect to y. Okay, now Hessian is assembly of all the double derivatives that you have. Okay, now for a two-dimensional function, if you think of, there are two dimensions x and y. Now you have written down all the possible uh, double derivatives that you have. Double derivative with respect to x, with respect to xy, and with respect to y, right? But these two terms are same basically. If you think of Hessian is, if you think of gradient as x speedometer, Hessian is basically the accelerator pedal for you, right? Because accelerator pedal, because if you think of rate of change of distance, dx by dt is your speed, then if you derivate it double twice, d2x by dt square is your acceleration, or let's say d by, if this is your speed, right? So ds by dt is nothing but your acceleration, right? So this basically tells you, Hessian tells you, how fast are your gradients changing, right? Acceleration tells you what? How fast is your speed changing, right? Hessian tells you how fast are your gradients changing. Gradient in terms of x direction, how fast is it changing in x direction? How fast is it changing in y direction? And how fast is it changing in both x and y direction? So Hessian tells you that. Okay. Now this Hessian is eventually used a lot in maximum minimum problem, to find maximum minimum. This is again other type of problem which is asked from this calculus, and this is actually simple, simpler than Taylor series problem. Because for example, if you have a single variable function. I'm just telling you the intuition first, and then we'll get into the second two variable function. Let's say fx is equals to minus x square. Okay, if you have to sketch it out, it actually looks like this: fx is equal to minus x square, right? Actually, x square looks like this, but because we are looking into minus x square, it eventually looks like this, right? So I will just remove that. Okay, now you already know that it has a maximum point at this point. But if you take a derivative of this function f dash x, remember to find maximum and minima in class 12th, 11th, I don't know which class, but I remember that we used to do it in some class, right? This becomes minus 2x. And what we used to do was f dash s, put it equals to 0, basically trying to find out a point where the slope is equals to 0. This is that point, right? So we are just trying to find out what is the derivative with respect to x and where basically it becomes 0. So we are putting it equals to 0. Hence, we are finding it out at x equals to 0. We found that the slope is 0 at x equals to 0. Now, because we found that x at x equals to 0, we don't know whether it's a maximum point or minimum point. To do that, we used to do a double derivative test, if you remember, right? You used to do f double dash at that point, let's say 0, whether the sign is positive or negative, right? If the sign is positive, what we used to do, and does anyone remembers that? If the f double dash is positive, what is basically the conclusion of what point is that, whether it's a maxima or minima? No one remembers that, is it?
Minimum.
If it is positive, it's minimum, right? If it is negative, it's maximum. Okay, so basically the criteria used to be, and I'll tell you the idea. The criteria is for one dimensional, the intuition is first find out f dash at a point x naught, okay, is equals to 0. Find that x naught point by just equating it. Okay, and then find f double dash x naught. If this f double dash x naught is greater than 0, then we say that it's a minima, right? And if f double dash x naught is less than 0, we say that it's a maxima. That is what we used to do, but there could be cases wherein f double dash x naught at that point where we found the slope was 0, it could be 0. Hence, we say that it's inconclusive. Conclusive. Okay. So these are the three different ideas or three different actually things that we found out. Once we find out, think of it as this is simple. I mean, you don't have to put more intuition to it. The slope could be 0 at these points, okay, for a function. You never would be able to know what these points are, whether it's a maxima or minima. The only way you can do is think of it as the only way you can do is how the slope changes around it. If the slope changes negatively, it means that you are already at maximum point because the slope is negative around it. And that's the rate of change of the slope is decreasing around it as you move from, let's say you have reached the Mount Everest. As you go down, your height is going to reduce, right? So the rate of change of your slope, rate of change of your height is going to actually decrease around that point. And hence we say f double dash x, if it is greater than 0, for example, let's say if it is less than 0, sorry, not in this, if it is less than 0, we say it's a maxima because we are already at the Everest, right? You are already at the highest most point. If the slope changes, if the slope value is negative, this value is negative, then you say that it's a maximum point. Now, counterintuitively, if you are here, let's say already reached, this is where the slope is 0. If the slope is changing positively, the function is attaining a more positive value, or let's say the rate of change, or let's say at this point, the slope is 0, right? If you see any point here, the slope is increasing both in both the directions. Hence, if the slope is increasing, f double dash x, for example, the rate of change of slope, this double derivative is nothing but the rate of change of slope. First derivative tells you the rate of change of function. Second derivative tells you the rate of change of slope. If the rate of change of slope is positive, the only way that can happen is if the function is concave upwards. This one, this way, right? Hence we say that this is that point. But now, given that you would have two variables, okay, you would have two variables, a function with two variables fx, y. So what you'll be doing, you will be first taking, think of it as, you'll be first taking the derivative of the function with respect to x, okay, first derivative, and with respect to y, you would equate them equals to 0, okay. Then you will get to some point x and y. You would then find out, let's say that point, whatever those points come out to be, then you will find out fxx, fyy, fxy. Okay, basically you will have to find out Hessian matrix. Okay, let's say for example your Hessian matrix, whatever those your Hessian matrix values are, let's say this is fxx becomes 2, this becomes fxy becomes 3, this becomes 3, this becomes, let's say, 1. Okay, now if you find the determinant of this, okay, let's say that determinant is equals to 2 minus 6, determinant is equals to 2 minus 6 is equals to minus 4. If determinant is negative, it means that you are at a saddle point. Saddle point as in a point which is neither maxima nor minima, but the function is changing. Okay, this point is a saddle point. It is moving from minimum value to maximum value, going from minimum value to maximum point. That change point is called a saddle point. So if your determinant is negative, it means that you are at saddle point. If somehow determinant is positive, let's say that you would have got let's say 10 here. Okay, now let's say 20 here, right? So 20 minus 9, 2 minus actually 9, it should be right. So 20 minus 9, then that value would have become 11, right? Because the determinant is positive, hence you can have both the things, maxima and minima. Okay, now it all depends on whether fxx, this first value, is positive or not. If fxx is positive, okay, you remember what we had. If fxx is positive, then you will have minima. If fxx is negative, then you will have maxima. So basically, all of these criteria is what I'll show it to you in one of the problems that I have written down here in your confident docs. Sorry, component doc. Let's say this is the function. Okay, what you'll have to do, you'll have to first find out what is the rate of the change of the function with respect to x. Now, if you derivate it with respect to x, you are just getting y minus 2x minus 2. This is what you have. You derivate it with respect to y, you get x minus 2y minus 2. Now, from these two equations, you can basically solve, you have two equations, two unknowns. You can substitute, eliminate, use those methods to find values of x and y. This is what we are doing here. Once we have found values of x and y, these are the two values. Basically, we have this point at which the slope is 0. Now we have to find out whether this point is a maximum point or a minimum point, right? To find that out, you'll have to find out double derivative or take a double derivative test. fxx, fyy, fxy, you have found all of them. Then you will find out what is the value of the determinant. Determinant is these fxx, fyy. Remember the cross diagonal element minus fxy square. This is how it comes down to, because the determinant is positive and fxx is negative, hence it is maximum. So this is what you do, and all of these criterias are mentioned here. If you see at the top, these are the criterias. Local minima, determinant is great, is positive, fxx is positive, minimum, right? Remember what I told you about in first dimension, 1D intuition. If this rate of change of slope is negative, it means that you are already there at the maximum point. And that's what you're seeing here. If the rate of change of slope is negative, you're already at maximum, right? So if determinant is positive, rate of change is negative, maximum. Determinant is positive, rate of change is negative, minimum. Okay. Saddle point, determinant itself is negative. Now to help you understand this, what I have done is I have shown it to you here. See here, this is the entire logic. So see, this is the Hagen matrix. Okay. Now we are computing determinant. If you are able to see on the right hand side, determinant is shown, right? Determinant is positive right now at that whatever stage. Fxx is 2. Determinant is positive. Fxx is 2 is positive minimum. You see the entire function, the entire two-dimensional function looks like this. Now if you see fxx negative, how, when can fxx be negative? Let's make it negative. Okay, fxx is negative. Okay, fxx negative, but see here, determinant itself is also negative. Now this is that saddle point, because in one direction, if you think of, in one direction the function is increasing. If you see here, the function is increasing in this direction, in y direction, but the function is decreasing in x direction, right? So you are having both of them in the same point, which is what we don't want, right? And hence in that case determinant would become negative. So this is that point wherein fxy, if you see here, fxy is actually 0, right? Because the in one way rate of change with respect to x is decreasing, rate of change with respect to y is increasing, and that is what we don't want. Okay, the rate of change with respect to x decreasing, a rate of change with respect to y increasing, 2 is the value. We don't want these types of scenarios. We want scenarios wherein fxx is, this is what for your machine learning problems, this is what is relevant. Okay, these types of situation wherein you have curved bowl type of a shape. Think of you have a bowl. If you have a bowl, it's easier to just slide a marble and get to the minimum most point. It doesn't matter where you start from, you eventually would reach to the minimum most point. But if you have a surface like this, think of it. If you have a surface like this, or let's say something like this, okay, how would you get to the minimum? I mean, if you start from here, it's easier to get here. But if you start from anywhere on this line where my cursor is, you are not, your gradient would die. Why I'm saying that is because if you think of your gradient descent, just a minute, your gradient descent is, no, what happens to my, your gradient descent is w new is equals to w old minus eta times of gradient of the loss function. Now at a flat surface, what would be the gradient? Low or high?
Zero.
What would be the gradient? Almost zero, right? If the gradient is almost zero, if this is zero, you are not making any progress. Or even if you are making progress, if it is almost approximately equals to zero, you will be just crawling, taking very small steps towards the minimum most point. So if you are here, somewhere here on this line, it will take infinite long to get to the minimum. If you are starting from here or here, you're good. But if you are somewhere here, you will eventually die out, right? So you will never be able to learn. The good part is we want a loss function which looks like this. Sorry, not this. Okay, yeah, somewhat like this. You want a loss function which looks like this. Because no matter which point you start from, you will be able to reach to the minimum most point, right? And hence the Bayesian matrix is important. Bayesian matrix, if determinant is positive and fxx is also positive, this is 0.8 if you see here, right? Then you know that there is only one minimum which is possible. Okay, given that it's a convex function. You see why this is all important, right? Good. Yes, no.
So if determinant is positive, we shall check fxx is positive, and we
Exactly.
not need to check fyy.
No, you don't have to. Think of it. See here. See here. If it is negative, determinant can be positive. When the determinant would be positive? Let me show it to you. When can determinant be positive in these cases? 2.24. Okay. Let me increase. Determinants positive, right? So you have a this particular case, a maximum case. You still have a bowl safe, but you are trying to find the maximum. Okay. So if you have a negative fyy, it means you're basically fxx is negative. Let's say fxx is positive, right? And you care about fyy, there could be saddle point. Let's say determinant is positive from only on these cases, right? After here, it is all negative. Determinant is positive here. You don't worry about, because your shape is all dominated by how the how does that fxx is changing.
Sir, x and fyy. So, why only fxx?
No. Actually, that determinant calculation is all based on fxx. But your logic, I mean, I know why you are all asking this question. This is relevant. Think of it as if you have a two-dimensional function just like this, right? And let's say that it increases in x. This is, let's say this is y, this is y. So you are trying to see what is the rate of change in y, what is the rate of change in with respect to x. Both the directions are important, right? And let's say this is how the bowl looks like, right? So both the directions, this direction is important, as well as this direction is important, both of them. Unless you are having increase in both the directions, you will not have a very good looking bowl. But the good part is, once you have a determinant, let's say fxx, fxy, fxy, fyy. Once you have a determinant is positive and fxx is positive. Determinant can only be positive when this multiplication. Think of it. Determinant always already takes into account fxx into fxy. Sorry, fxx into fyy. This is what you'll be doing, multiplying minus fxy whole square. This is what the value of determinant, right? If you are saying the determinant is positive, basically you are saying this should be greater than 0, right? Basically you are saying that fxx into fyy is greater than fxy square, right? Then only determinant could be positive. Or you are saying that the multiplication of these two is greater than what cross element that you get, right? So let's say this can only happen if you have these two large positive. If these two are large positive, then only you can overshadow fxy square, right? Hence, that if determinant you have already taken as positive, no need to take the f or lay out a new criteria saying that fyy also needs to be positive. You just can say that fxx is positive. If fxx is positive, okay, then in that case, fxy, to make this entire thing as greater than, it needs to be positive ultimately.
So, but if both fx6 and fx6 and fyy are both big negative numbers, then also it can be greater than fxy square, because fxy square is a positive number.
Yeah, that's so think of it as what would happen. Okay. Let's say that you are saying that this is -8, this is -6. Let's say this is 2, this is 2.
Yeah.
Right? So think of it. 8 into 6, 48, right? 48 minus 4, right? 44 is what you will be getting. But this is positive, right? But fxx is negative, -8. What you are saying? You are saying that rather than looking into the minimum point, you are now looking at a maximum point. That's what it says. Because it says that it is decreasing in both y and x direction, the function, the double derivative. Remember the x square example that I gave? If you are at exactly at the highest point,
That will be a local maxima.
That would be a local maxima. Exactly. That's right. That would be a local maxima. If you think of it as here in, let's say this is negative and fyy is negative, highly negative. This is what you will be having. Determinant is still positive. Right?
Thank you, sir. Thank you.
And Saurabh,
So
what
these
if
Hessian
fx is
matrices are always symmetric, right? Hessian matrix?
Yes. This is always symmetric.
Symmetric.
Sir, what if fxx is 0, right?
Fxx is 0. For example, if you take fxx as 0, this is that point. Sorry. This is that point, right? Now, if you have fxx as 0, so basically what different cases can be, either it can be a saddle point or a degenerate solution, basically a flat surface. Either it would be a saddle point, like the function changes. The function changes. It will never be a maximum or minima.
Right.
No matter what your fxy are, if both of them are negative, and in that case, let's say whatever, let's say if one of them is 0,
Determinant would be always negative, right? In that
right?
case.
Yeah, exactly.
Right.
Sir, just one more thing, just for a summary perspective. So along with determinant value as positive, we are also considering fxx and fyy value as well, right? Positive or negative.
You don't have
Okay.
to consider fyy, you just consider fxx.
fxx.
That's all. These in the component doc, I have written down all of these things, and do practice these problems. I mean, these types of problems which I have written down here in the component docs. This is old document, 2 years old, but the problems are still relevant. Okay, so these types of problems are what you will be asked in the exam. Please do practice these problems. Anyways, I'll give you a practice document, but you can expect similar types of problems in your exam. And these are again simple derivative based questions. If you know how to derivate a function well, first order derivative and second order derivative, how to find that out. I mean the partial derivatives. No one is going to give you a simple one variable function. It will always be a two variable function, that is almost certain. So practice these types of problems more. Okay.
Sir,
Can you please share the HTML also after the session?
Yeah, I'm going to upload it. Yes.
Sir, last week you were telling us some derivatives of some common functions like ddx of sin x, ddf of cos x, tan x. So it would be good if you can give us some this type of common derivatives. It will be helpful.
Right.
A list.
Right. I had a cheat sheet. I don't know whether
A list of common derivatives which can come. So that is it.
Okay. Yeah. I think I had it. I did share cheat sheet Mfml PDF. Yeah, I think this is 10th Jan 2026. Okay, I think this is the one. You can go through it. Actually, you will. No. This has all of them, but it doesn't have the functions. I think this will help you. Calculus not there. It's not there, but I'll give it to you. I'll add it here in this. Okay. I think I gave it somewhere, but I don't remember where it is. I will share it with you.
Thank you, sir.
Okay. Yeah, I think this is the one. Here you will get all of those things. A simple before this is all of those rules, right? You need to know all of these.
Yes, sir.
This is what I'll share it with all of you.
Yes, sir, please share both.
Sir, can you share both?
And
Yeah.
if you have for ML also, you need to be helpful for
So this
us.
completes the syllabus, or like we will have one more class tomorrow, right?
That class is, we have a class tomorrow, but that class is on chain rule and back propagation. There are very less chances of questions being asked from both of them, but we eventually be that's a part of the syllabus. So we'll cover that. There are only 19 slides. We'll go slow, but we'll cover that.
So then tomorrow, can we have
Sir,
some
in the
similar
Hessian,
questions patterns done maybe in the
Yes,
class
yes,
itself?
I can.
Yeah.
Yes, in one, that's what I thought.
Yeah.
In the first half, I'll cover what is required from for covering the session point of view. Then the second half, I'll cover most of these different types of questions which keep repeating every year. I'll give you those intuition idea.
Thank you, sir.
Okay.
sir, in the Hessian matrix, we have fxx and fyy, and in the other diagonal, we have fxy in both corners. So why not fyx? Like, are
No,
they
it's a,
same
it's the
or?
same thing. It's the same thing. Fxy
Okay.
or fyy is the same thing. Think of x square plus 3xy plus y square. Okay. If you take fxy, you eventually would get to 3. If you take fyx, you eventually would get to 3. Both the things are same.
Will it be true for all functions? Like
Yes,
even
yes,
for
it's
radial
true for
things?
all.
Okay.
Yes,
Okay.
yes.
Okay.
Okay.
Sir,
And
when you show the matrix, right, and in that visual HTML, how we can point those values with respect to 0, minus 3, minus 3, minus 2.7?
this one.
Yeah. In the graph, in this one. Yeah.
Okay, let's say for example, you have this, right? 3 and you have fxx. You can choose any one of these. So let's say the both are positive. So this is how it would look like. So let's say, I mean, I should have made it more something like I should have given more choices to go from minus 10 to 10, but it is and currently going from minus 3 to 3 only. But anyways, you can change these values fxy. You have fxy here. Okay. And fyy here, you can change it via slider here. You have the good part is you have all the different cases that can come in from your idea, intuition, exam point of view. Bowl shape, what can happen? And you have a dome shape, maximum, saddle point. You do not have a solution there. Sorry, not solution, as in you neither have a maxima nor have a minima, but still the slope is 0. Okay, twisted. This is how it would look like. Degenerate solution, settle point, sorry. And then flat valley. This is what we also looked into, wherein in one direction there is change which is happening. In other direction, the change is not happening at all. Right. So if you would want to look into like spinning it, like you have all of those things. But anyways, this is how you can do all of these things.
Sir, gradients of vector
Can we
valued
conclude
function.
about
Okay,
go
sir,
ahead.
gradients of vector valued functions, right? The Jacobian one.
Right.
Will we be covering that in
Yes, yes,
tomorrow?
tomorrow. Yes, yes. We'll start
Okay.
with that only. Okay.
Okay. Then computing maxima and minima for unconstrained optimization.
That is unconstrained. Think of maximum minimum for unconstrained. If you have x square minus 3xy plus y square, you have an unconstrained problem. Okay. You don't have constraints here. You will learn about constrained optimization problem post midsems. This is an unconstrained problem because you do not have any constraint. You just have to find out maximum and minimum of this. So the problem, the in your handout, if it says unconstrained optimization, unconstrained maximum, these are the type of problems that we were discussing till now. So that was the part.
Okay, okay. Thank you, sir.
Okay.
Sir, using Hessian, we can conclude about local minima and maxima. Can we also conclude about global minima
No,
and maxima?
never, never, never. You can never. I mean, you can never do that. You will never be able to find that out.
So the only way to find out is using double derivative.
You basically say think of it as you will have to evaluate every point. Okay. Let's say I'm just telling you an intuition. Let's say this is a function. You have slope 0, 0, 0, 0, 0. Okay. You will have to evaluate at this point, at this point, at this point, at this point, at this point. If your minimum, if you are trying to find out global minimum and you are basically finding it at this point, you will be able to find what is the minimum most value at this point. So you would be able to find that out eventually, but you will have to evaluate at all the points. Okay, or all the points. Basically, what we do, you try taking fx, let's say if it is one variable function, so you take f dash x is equals to 0. Okay, just like x square plus 4x. Let's say that this is the function. You take the derivative of this, you get 2x plus 4 is equals to 0, or x is equals to minus 2. So basically x is equals to minus 2 is the point where the slope is, or let's say this is the function, right, where the slope is 0. This is that point. X is equals to minus 2. Let's say that this is minus 2. And at this point, the slope is 0. But eventually you have got only one point. There are chances, let's say the function could have been x to the power 6 plus 5x square minus 2x plus 4 is equals to 0. Now this type of a 6-degree polynomial could have 6 roots, let's say minus 3, 2, 1, 4, right? Now, because of all of these roots, you will check against all of these roots what is the value of the function at all of these points, and then you will get to know what is the minimum most point. But when you have multivariable function, let's say f x, y, z, in that case, you will have to find out fx, fy, fz, equate them equals to 0 to get to the point first. Get at what point the slopes are 0, right? Then you will get to the point. Let's say there are 3 different points that you get to, p1, p2, p3. You will evaluate at p1, evaluate at p2, p3. Let's say out of these two are maximum and one is minimum. Basically the function, two-dimensional representation of the function would look like this. Okay, these two are maximum. There is only one minimum, which is here, right? So you are able to see the minimum most point, which is this. So these two are maximum, which are these 2 points that you are able to see. But then you will have to find out at whatever point 1, point 2, point 3, what is the value of the function? What is the minimum most value of the function? Once you can conclude that minimum most value of the function, there is one minimum, obviously it is going to be P3. But if there are multiple minimums, let's say P4 and P5 are also minimum, basically the function looks like this. Let's say that this is how the function looks like. So this are minimum. P3, P4, P5 are minimum. In that case, all of these you will evaluate and find out at what point, either P3, P4, P5, what is the minimum most value of the function at these points. Then you will be able to know directly using substituting the value of the points in the function directly. What I'm trying to tell you is eventually you have a function like this xy plus x square, right? And you have found x is equals to 2, y is equals to 1 as one of the points. Substitute that. And let's say another point as x is equals to 4, y is equals to 4. Substitute that. Find which particular point is the minimum. Whether x is equals to 2, y is equals to 1 is the minimum most point, or x is equals to 4, y is equals to 4 is the minimum most point for this function. Okay, obviously this one would be because it's all positive values. But anyway,
First identify the point, then evaluate each
exactly.
point.
Exactly
Okay.
right. That's right.
Got it, sir. Thank you.
Okay. Good. I
Sir,
think
just one
yeah,
quick
go ahead.
question.
Go ahead.
In one, your companion, you show that uh, differentiate with x and y, then solve the equation to get the value of x and y. And at
Right.
one, we have one question where we know the first point. So
Right. Which one is that? Let me go to that. This one, right? The second problem.
yeah,
This one.
this one.
Right. So basically, if you think of y is equals to, we have found out this equation x into x cube minus 1 is equals to 0. Basically, x to the power 4 minus x is equals to 0 is the equation which formed out. And we found that x can be either 0 or x can be 1. Okay. Now, because x is 0 or 1, y can have two values. So your critical point becomes 0 and 0, 1 and 1. Now, what you are trying to basically, these are the two points that you have found out. Now you will evaluate double derivative fxx, fyy, fxy. Now you found using fxx at x is equals to 0, y is equals to 0. Fy x equals to 0, y is equals to 0, fxy x equals to 0, y is equals to 0. You have found that out. These are the values that you have got. And then you find out the determinant value. You found the determinant value using Hessian. You found that determinant is less than 0. Because determinant is less than 0, the only condition where the determinant is less than 0 is a saddle point. You already know about it. Hence, it's a saddle point. So this point, if you think of whatever way method that you know, the only thing that you will have to do is you have two equations, two unknowns, get to finding the points at which the slope is 0. That's the essence, that's the idea. So whatever you know to find out the values of x and y at which the slope is 0. And that's why we are derivating it with respect to x and y and then equating it equals to 0. So you could know the method. Let's say in this particular case, we found out y is equals to x square, x is equals to y square. Okay. Now, if you take a look into x is equals to x square, let's say if you take x is equals to x square in the second equation, if you feed in y is equals to x square, right? So in this particular case, x square would look like this. So I'm just helping you in making it understand that there could be various different ways you could have solved these two equations, but the good part is the final destination is you have to get to these points somehow. Whatever method you use, what you get to, these critical points has to be same for all of us and the way we are evaluating, right? What method you use, it eventually is not important, but what points that you get to is important. The critical point has to be correct. Even the next case as well, if you think of this problem, right? This one, this is all the three problems are of three different shapes, three different types. You'll get to know why I'm saying, because if you will solve the last problem, I'll not tell it to you. But if you solve this problem, you will get to know about it.
Okay, sir.
Okay. I think we are good. We'll meet tomorrow. I'm also all done. Sorry about it.
Thank you, sir.
Thank you, sir.
And thank
Thank
you.
you.
Thank you. Thank you.
Yes, sir.
Thank you all.
Thank you, sir.
Thank you.
Please share
Thanks.
the cheat sheet, sir.
Yeah,
Thank you,
yeah,
sir.
yeah. I will.